Welcome to our exploration of the laws of motion. Today we'll break down fundamental concepts that govern how objects move and interact. We'll start by looking at velocity time graphs, which visually represent how an object's speed changes over time. These graphs help us understand whether an object is accelerating, decelerating, or moving at a constant speed. Examining these graphs, we can match real-life scenarios to their graphical representations, making abstract concepts much more tangible. As we progress, keep in mind how these visual tools connect to everyday experiences, such as driving a car or watching a ball roll. Let's dive deeper into the differences between distance and displacement, and uniform versus non-uniform motion to build a solid foundation for understanding movement. Let's clarify the difference between distance and displacement. Distance is the total length an object travels regardless of direction, while displacement measures how far out of place an object is, its overall change in position. For example, if you walk around a block and return to your starting point, your distance is the total path you walked, but your displacement is zero because you ended up where you started. Distance depends only on magnitude, making it a scalar quantity, whereas displacement depends on both magnitude and direction, making it a vector. Diagrams can help illustrate these concepts, showing paths and shortest distances between points. Understanding this distinction is crucial for analyzing motion and solving physics problems. Next, we'll look at uniform and non-uniform motion to see how velocity affects movement. Now let's distinguish between uniform and non-uniform motion. Uniform motion occurs when an object covers equal distances in equal intervals of time, meaning its velocity remains constant. In contrast, non-uniform motion happens when the object's velocity changes, so it covers unequal distances in equal intervals. For instance, a car cruising steadily on a highway exhibits uniform motion, while a car stuck in traffic, speeding up and slowing down, shows non-uniform motion. Graphs and diagrams can visually represent these differences, helping us see how velocity changes over time. Recognizing these types of motion is essential for understanding how forces and acceleration come into play. Next, we'll apply equations of motion to solve practical problems and see how these concepts work in real-world scenarios. Equations of motion are powerful tools for solving physics problems. The first equation v equals u plus at relates final velocity, initial velocity, acceleration, and time. The second equation s equals up plus 1 2 at 2 helps calculate the distance traveled. The third equation v2 equals u2 plus 2 as connects velocity and distance. By plugging in values, we can solve for unknowns like final velocity, initial velocity, acceleration, or distance. For example, if a car accelerates from rest, we can determine how far it travels in a given time. These equations are not just theoretical, they're used in engineering, sports, and everyday life. Understanding how to apply them makes analyzing motion much easier. Next, we'll explore key terms and scientific reasoning behind motion, such as deceleration and momentum. Let's clarify some important terms and their scientific explanations. Displacement is the minimum distance between start and finish points. Deceleration is negative acceleration, meaning velocity decreases over time. In uniform circular motion, velocity changes at every point because direction changes, even if speed stays constant. During collisions, total momentum remains constant, illustrating the law of conservation of momentum. Working of rockets depends on Newton's third law. Every action has an equal and opposite reaction. When an object falls freely, its acceleration is uniform near Earth's surface. Action and reaction forces don't always cancel because their points of action may differ. It's easier to stop a tennis ball than a cricket ball at the same speed because the cricket ball has more mass and momentum. An object at rest is considered to have uniform velocity, zero, but constant. These concepts form the backbone of motion analysis. Newton's laws of motion are everywhere around us. The first law, inertia, explains why a rock stays at rest until pushed. The second law, F equals ma, shows why a heavier object needs more force to move. For example, a truck and a bicycle racing at the same speed will behave differently due to their masses. The third law, action and reaction, is seen when rockets launch. Burnt fuel pushes down and the rocket moves up. Everyday examples include pushing a floor, car wheels producing friction, and a dog pulling a rock. These laws help us understand everything from sports to transportation. By observing our surroundings, we see physics in action, making the subject more relatable and practical. Next, we'll solve some real-world problems using these principles. Let's apply what we've learned to solve some practical problems. For instance, calculating average speed involves dividing total distance by total time. If an object moves different distances in equal intervals, we add up the distances and divide by the total time. When force and mass are known, we use F equals ma to find acceleration. Conservation of momentum helps us determine the velocity of objects after a collision, such as a bullet embedding in a plane. These calculations show how physics principles translate into real-world scenarios like swimming, driving, or sports. By mastering these methods, you can analyze and predict motion in everyday situations. Understanding these examples reinforces the importance of the laws of motion and their applications.